Consider a student with an impeccable academic record. They max out standardized tests and ace every written exam. But put them in an unstructured, fast-paced crisis, and they freeze. They possess deep analytical knowledge, yet lack the capacity for autonomous problem-solving or original ideation. This happens because modern education operates as a closed system. Schools have engineered an isolated environment that explicitly rewards rote memory and strict analysis, while actively ignoring other cognitive demands. Over time, the metric replaces the goal. The standardized test, originally designed as a predictor of future performance, becomes more valued by the system than the actual real-world performance it was supposed to forecast. By conflating a narrow set of test-taking skills with general intelligence, our educational infrastructure inadvertently sets its brightest analytical minds up to fail the moment they leave the classroom. This diagram maps the restrictive feedback loop of that current system. An incoming student is filtered entirely through memory and analytical tests, producing a binary outcome of high or low tracking, completely sealed off from external variables. Psychologist Robert Sternberg proposed an alternative, the triarchic theory of successful intelligence. In this model, intelligence is not a single monolithic general factor, but rather the integrated ability to adapt to, shape, and select environments. The first pillar of this theory is analytical intelligence. This is the conscious direction of mental processes to evaluate information and solve predefined structured problems. The second pillar is creative intelligence. This is the capacity to invent, discover, and generate entirely novel ideas when no clear instruction exists. The third pillar is practical intelligence. This is the street-smart ability to read an environment, apply knowledge effectively, and execute solutions. True intelligence requires a balance of all three. A successfully intelligent person figures out how to capitalize on their specific strengths across these domains while actively compensating for their weaknesses. This radar chart maps three student archetypes. Alice is purely analytical, maxing out test scores but lacking original ideas. Barbara is highly creative, but low aptitude scores overshadow her stellar portfolio. Celia has average academics, but maxes out practical execution, dominating the job market. The current closed system explicitly selects for the Alice archetype. In doing so, it systematically filters out the creative potential of students like Barbara and the practical execution skills of students like Celia. Standardized assessments do not measure a student's total capacity for success. They merely measure compliance with a highly restricted, artificial set of cognitive demands. To understand how intelligence depends on environment, look at a study involving the Kapelle tribe in Africa, which challenges Western assumptions of cognitive superiority. Researchers asked Kapelle adults to sort objects. They sorted functionally, pairing an apple with the act of eating, a method Western tests score as incorrect. Yet, when researchers finally asked them to sort how a stupid person would do it, the adults instantly executed the exact taxonomic sorting the Western test demanded. A similar disconnect appears in Usenge, Kenya, where researchers investigated how school-age children adapted to their indigenous environment. The data revealed a startling anomaly. Researchers found a statistically significant negative correlation between a child's practical knowledge of survival herbal medicines and their scores on Western academic tests. The better they understood their actual environment, the worse the school deemed their intelligence. This mirrors findings among Brazilian street children. These youths run complex, mathematically demanding street businesses to survive. Yet, when researchers presented them with identical mathematical operations formatted abstractly in a classroom, the children failed them. What we typically call the general intelligence factor is largely a cultural artifact of Western schooling. True intelligence is inextricably bound to a person's ability to adapt to their specific survival context. Educators often raise a valid concern. If we shift instruction to include creative and practical skills, will students' performance on standardized memory and analytical tests drop? This chart compares Sternberg studies testing baseline memory instruction against triarchic instruction, which matches teaching to cognitive profiles. The results? Triarchic students surpass the control group in creative and practical performance and even beat them in conventional memory and recall tests. The cognitive mechanics explain why this works. Encoding material through multiple lenses, analytical, creative, and practical, allows students to process information using their natural strengths, making the underlying facts much easier to retain. The empirical reality is clear. Triarchic instruction is scientifically superior to rote memory teaching, even if your only goal is to maximize the recall of factual knowledge. To apply this in the classroom, we have to break down the first steps of the analytical cycle. True analytical instruction begins not with answering a question, but with accurately identifying the problem. For years, U.S. automakers complained that Japanese trade laws were the reason their cars failed to sell in Japan. The actual problem was that U.S. manufacturers tried to sell cars with the steering wheel on the left side to a country driving on the left. We see this in crisis management. During the Watergate scandal, the administration misidentified the core problem, focusing on the cover-up rather than coming clean. In contrast, when Tylenol faced a poisoning crisis, they accurately identified the threat to public trust and immediately recalled their product, securing their long-term market dominance. Once the problem is identified, the second step is allocating resources. Problem solvers must partition limited time, effort, and capital strategically before executing a solution. In a study on reading comprehension, researchers found that expert readers allocated their time specifically based on their end goal, skimming for the gist versus reading slowly for deep analysis. Poor readers, however, distributed their time arbitrarily, regardless of the task. Effective analytical instruction requires forcing students to accurately frame the problem and budget their cognitive resources before they ever attempt a solution. The third and fourth steps in the cycle are representing the information and formulating a strategy. How data is organized entirely determines the success of the sequence. In the early days of personal computing, IBM formulated a strategy around an open system. Allowing clones encouraged massive software expansion and secured market dominance. Apple initially took the opposite approach. Formulating a closed proprietary operating system strategy severely limited early software development and caused their market share to decline. The pedagogical rule derived from these steps is specific. Expert problem solvers devote significantly more time early in the cycle to representing the problem and plotting a strategy, which saves them critical execution time later. We must bring this architecture back to the classroom. By explicitly teaching students to sequence and strategize, we move them from impulsive guessers to reflective analysts. The closed loop of conventional education can be broken. Educators must stop conflating a student's ability to navigate a highly artificial, closed testing loop with their total intellectual capacity. By expanding instruction to balance analytical, creative, and practical abilities, we do not abandon academic rigor. Instead, we fulfill the ultimate promise of true education, preparing students to thrive in a complex, unpredictable reality.